For single mode fiber, the critical value of normalized frequency for the parabolic profile graded index fiber is increased by a factor of √2 on the step index case. This gives a code dia increased by a similar factor for graded index fiber over a step index fiber with the equivalent core refractive index and the same relative refractive index difference. The maximum V number which permits single mode operation can be increased. Still, further, when a graded index fiber with a triangular profile is employed, so depending on the application, you can change the profile. That alpha value of the index can be manipulated to get the advantages of that particular design. It is apparent from that the increase in this case is by the factor of √3 over a comparable step index fiber. Hence, significantly large code dia single mode fibers may be produced utilizing this index profile. Such advanced refractive index profiles, which came under serious investigation in the early 1980s, have now been adopted, particularly in the area of dispersion modified fiber design that will be discussed later on. But one of the major application of graded index fiber we can see for the design of single mode fiber, where we can increase by some factor, we can increase the code dia, right? Because smaller code dia fabrication is really difficult, and to maintain the refractive index within that small region, it is also very difficult. So it will be easier for us if we use uh, the graded index fiber for single mode operation. That will be easier for fabrication as well as for the design. A further problem with single mode fibers with low refractive index difference and low V values is that the electromagnetic field associated with the LP10 mode extend appreciably into the cladding. That's the biggest problem, because that will increase the effective code dia. Okay. For instance, with V values less than 1.4, over half the modal power propagates in the cladding. Thus, the exponentially decaying evanescent field may extend significant distances into the cladding. It is therefore essential that the cladding is of suitable thickness and has low absorption and scattering losses in order to reduce attenuation of the mode. That means not only the core, we have to take care of the cladding as well. That's the problem. Estimates show that the necessary cladding thickness is of the order of 50 micrometer to avoid prohibitive losses greater than 1 dB per kilometer in the single mode fiber, especially when additional losses uh, resulting from microbending are taken into account. So the total fiber cross section for single mode fibers is of a comparable size to uh, multi-mode fibers. So another approach to single mode fiber design, which allows the V values to be increased above 2.405, is the W fiber, the shape like a W, right? The refractive index profile for this fiber can be drawn in this way. So first, from the core we have N1, then it will be N2 for certain range of certain range, and then it will change to N3. Okay, so this is how the index will vary. So use of such two-step cladding allows the loss threshold between the desirable and undesirable modes to be substantially increased. The fundamental mode will be fully supported with small cladding loss when its propagation constant lies between the range kn3 to kn1. So propagation coefficient will be between kn3 and kn1. So this is the index profile W. It is one side of the W actually. Actually, we should have to plot in this direction also to get the full W. Okay. However, this type of uh, variation of refractive index in both core and cladding will give us some extra flexibility and extra performance parameters for the fiber, and we will discuss these things later on when we'll discuss different kind of fibers available in current scenario. If the undesirable higher order modes are excited or converted to have values of propagation constant where beta less than kn3, they will leak through the barrier layer between A1 and A2 into the outer cladding region N3. Consequently, these modes will lose power and by radiation into the lossy surroundings. This design can provide single mode fiber with longer core dia than can the conventional single cladding approach, which proves useful for easing uh, jointing difficulties. W fibers also tend to give reduced losses at bends in comparison to the conventional single mode fibers. Following the emergence of single mode fibers as a viable communication medium in the early 80s, they quickly become the dominant and most widely used fiber type within telecommunication system. Major reason for this situation, that is why we are going for single mode operation, they exhibit the greatest transmission bandwidth and the lowest losses in the fiber transmission media. They have a superior transmission quality over other fiber type because of absence of modal noise. They offer a substantial upgrade capabilities, that is the future proofing for future wide bandwidth services using either faster optical transmitters and receivers or advanced transmission techniques. They are compatible with the developing integrated optics technology. The, this these regions, reasons provide confidence that the installation of single mode fiber will provide a transmission medium which will have adequate performance such that it will not require replacement over an anticipated lifetime of more than 20 years. That means once you lay the fiber, whatever may be the upgradations, that fiber will work, that fiber will be compatible to all those upgradations within nearly uh, 20 to 20 years or more than 20 years. So it is very, very flexible. Okay, so that is why people have shifted from multi-mode operation to the single mode fiber over the time. Widely deployed single mode fibers employ a step index or near step index profile design and are dispersion optimized. We will discuss those things later on for operation in the 1.3 micrometer wavelength region. Those fibers are either of a match cladding or depressed cladding type of design. In the conventional match cladding fibers, the uh, region external to the core has a constant uniform refractive index, which is slightly lower than the core region, typically consisting of pure silica. So single mode step index profile optimized for operation uh, like this one. It is a conventional match cladding design, this type of profile. And this is the segmented core match cladding design. An alternative match cladding fiber design employs a segmented core like this one. So such structure provides standard single mode dispersion optimized performance at wavelengths around 1.3 micrometer, but is multimoded with a few modes, not much mode, but a few modes will be there in the shorter wavelength region around 0.8 micrometer. So if we use this particular fiber from, instead of using it in 1.3 micrometer, if we use it in 0.8 micrometer region, then it will be almost single mode. Only a few, one or two modes, two or three modes will be there, but its performance will be much better than conventional multimode fibers. The multimode operating region is intended to help relax both the tight tolerance involved when coupled LEDs to such single mode fibers and their uh, reconnectorization. So segmented core fiber of this type provides for application which requires an inexpensive initial solution but upgradability to standard single mode fiber operation fiber performance at 1.3 micrometer wavelength in the future. So this is uh, the kind of segmented core match cladding design profile. Now these are another kind of um, profile, that is the depressed cladding design and profile specification for depressed cladding fiber here. So in depressed cladding fibers, these depressed cladding fibers, the cladding region intermediately adjacent to the core is of a lower refractive index than that of outer cladding region. A typical MFD of a DC fiber is 9 micrometer with positive and negative refractive index, relative refractive index difference of 0.25 and 0.12%. So basically what the intention of this whole thing is to show that we can perform lot of engineering in with the help in refractive index, right? So both in core as well as in the cladding, and by using this such techniques of changing refractive index, etc., we can have better performing fiber, we can design better performing fibers and fibers for various other applications as well.